Hello everyone, we are Team LogicX. In modern drone systems, accurate navigation is critical. However, most drones rely entirely on GPS. The problem is GPS signals are extremely weak and easily blocked. In real-world situations, like indoor environments, urban cities with tall buildings, tunnels, or even war zones with electronic jamming, GPS fails completely. For example, during recent conflicts, GPS jamming has caused drones to lose navigation and fail within minutes. When this happens, drones experience high latency, position errors, and completely loss of control. So the problem we are solving is, how can we achieve reliable and accurate drone navigation in GPS-denied environments? Currently, when GPS fails, drones rely on IMU sensors. IMU tracks motion using acceleration and rotation data, but it has a major limitation called drift. This means small errors keep accumulating over time, leading to large position errors. Within seconds, the drone becomes unstable and unsafe. So, IMU alone is not a reliable solution. To solve this problem, we designed a multi-source navigation system. Our system combines two technologies: LEO satellites for strong and low latency positioning, IMU sensors for continuous motion tracking. These two inputs are fused using a Kalman filter to produce a highly accurate position estimate. This creates a robust and GPS-independent navigation system. In our architecture, the LEO satellite sends positioning data to a PNT receiver. The IMU continuously provides motion updates. All these inputs are processed by the Kalman filter. Finally, the fused output is sent to the flight controller to guide the drone. This entire system is modeled and simulated using VisualSim Architect. Using this device, we collect real-time data for drone navigation and analysis. The system is built around an ESP32 microcontroller, which acts as the main processing unit. The device integrates multiple modules. It includes a GPS module, which provides location data such as latitude, longitude, and altitude. An IMU sensor, specifically the Adafruit BNO085, is used to capture motion data like orientation, acceleration, and rotation. All the collected data is stored locally using an SD card module. This enables continuous data logging during drone operation. The system is powered by a 3.7-volt battery, making it compact and suitable for onboard use. After data collection, the stored data is extracted from the SD card and converted into CSV files. These CSV files are then given as input to VisualSim simulation software. Using VisualSim, we process the data and generate graphs to analyze the drone's movement, position, and overall behavior. In summary, this system captures sensor data, stores it, feeds it into VisualSim, and helps us visualize and understand drone performance. Here, we are using VisualSim to simulate our system. This block represents the LEO satellite source. This is the IMU sensor generating continuous data. At the center, we have the Kalman filter, which fuses all inputs. Finally, the flight controller processes the output. Now we run the simulation to analyze system performance. This graph shows the end-to-end latency and performance of the system. In scenario 1, with normal LEO operation, latency is around 32 milliseconds and performance is stable. In scenario 2, during a satellite handover gap, latency spikes up to 85 milliseconds and position error increases to around 0.30 meters due to IMU drift. This is a 6 times improvement in accuracy. This clearly shows that sensor fusion significantly improves system performance. Our key findings are: GPS is unreliable in denied environments. IMU alone is not sufficient due to drift. LEO provides stable and low latency positioning. Sensor fusion is essential for accuracy and safety. We have also identified that the Kalman filter is the main system bottleneck, which can be optimized further. In conclusion, we developed a GPS-independent drone navigation system using LEO satellites and IMU. Our solution achieves high accuracy and stable performance even in challenging environments. This approach is highly useful for applications like disaster response, defense operations, and autonomous navigation. We are not just improving GPS systems, we are creating a reliable alternative for the future. Thank you.